Hey. Okay, so my technical issue is resolved. So good afternoon. Today we'll continue the lecture on memory management. So last time we talked about the main goals being protection and allocation. So today we're going to talk about protection, and if we have time, we'll talk about allocation as well. Okay, so set this up. Okay, so just a recall, this is from the operating system concepts. So we talked about address spaces. Just a recall, an address space is a set of accessible addresses and their state, basically what is stored in those addresses. A physical address is basically what you have in your system. It's a data storage medium. And physical addresses are the addresses for the available addresses for your physical memory. If you have a 4 GB memory, as you saw in the previous lecture, this means that you have 2 to 32 bytes. And assuming that each byte is addressable, this means that you have about 4 billion addresses to use. If you have 16 gigabyte of RAM, so we can do the math. So 16 gigabyte is basically 4 times 4 gigabyte, and 4 gigabyte was 2 to 32 bytes. So that's 2 to 34 bytes. So this is how many different addresses you're going to have, 2 to 34. Then the topic of virtual addresses comes into picture. So virtual address is basically any address that is generated by the program, and if you have a system that supports 64 bits for the address bus, it means that programs can generate 0 to 2 to 64 bit from 0 to 2 to 64 different addresses. So if each address corresponds to a byte, then you have 2 to 64 bytes of virtual address, or virtual memory, sorry, which is huge, right? So before we get into talking about protection, I want to walk you through what happens when you start running a program. This will help us in the lectures to come to kind of have an idea about memory management. So the first step is that you have a source code, and then you compile your source code. The compiler takes as an input a single file, and then it creates a binary file from that source code. This is called an object file. The things that we have to be careful about this is that the compiler doesn't have a whole picture. So the compiler only sees your source code, and in your source code you might have used certain library routines like printf, like cout, cin. The source code for those functions are not necessarily included in your source code. They reside somewhere else. So as a result, the compiler will have to address some external objects in the object file. And this means that the compiler doesn't have the whole picture. So it doesn't know the address of certain functions. So it cannot create the end result. It cannot create the entire, it cannot map the entire address, because it doesn't know when it's compiling your file where the code for printf resides, or when where the code for, I don't know, a cout or cin reside. So this requires then another step where we put bunch of object files to create a single loadable and executable image. So that would be the job of the linkage editor in usual Unix systems. So this basically combines bunch of objects, bunch of object files to create a single executable image. What could happen here is that you could potentially rearrange the address space, right? Because when you, for example, compiled one file, you had certain code, certain data, certain inputs. So they might have been arranged in a certain way. Then you have another object, and now you want to merge all of them. So you probably want to put all the code in one place, all the data in one place, and so on and so forth. So this might mean that you're going to rearrange the address space for each one of those particular objects to come up with a unified address space for the entire thing. Next step is the loader. Now, the loader, the job of the loader is to get one of these executable images and load it to memory and make it ready for execution. Now, this requires the loader to allocate some memory space for this executable image. And then it also requires it to figure out a way to transfer control to the beginning of the instruction, the first instruction to be executed. Now, so one step further after loading is dynamic linking. So the dynamic linking, what it does is it dynamically loads or links the shared libraries that you have. So if you have, for example, clib, if you have clib, you probably don't want to link clib to every code that uses printf, right? So sorry, not this one. So this one, the linkage editor, it's going to take a bunch of object files and create a loadable module. Now, in this loadable module, you don't probably want to have a copy of clib, because if you have a copy of clib in any program that uses printf, then you're going to be wasting memory, because each module is going to be a huge module that has the entire, let's say, code for printf or clib or whatever library you're using. So you want to load libraries when they are needed. So when the program calls a certain code, you want to wait for that moment, and then at that moment link the code for that library to your loadable image. Now, for doing this, you're going to first look at your memory and see if you have clib before. Maybe you're the first code that is using clib. In that case, you have to bring clib. So dynamically at this point, the operating system brings the code for clib if it doesn't exist. If it exists, then it goes to the code and makes certain changes to map a certain area of the virtual address to the already existing clib library in the memory. Now, looking again, another recall, looking at how virtual address space is organized, you should remember that at the bottom of your virtual address space, we had the binary code. Then we had the initialized data. Then we had uninitialized data. Then we had the heap. And on top, we had the environment variables, and then we had the stack, which are the variable which is used for the variables in functions. Now, if you remember from the past, I mentioned that the shared libraries such as stdio, stdlib, iostream, or any other library that you want is going to be mapped between the stack and heap, because this is a free space. This is a virtual space that is free initially. So when you do dynamic linking, you are going to, or operating system is going to look at the virtual space of this program and find a free region of virtual addresses big enough to put the shared library. Then it will map that virtual address range to the library, so that the program from now on, whenever it wants to use the functions in that library, addresses the virtual addresses in this range. So this mapping happens dynamically. It could be for program A. So let's say we have two processes, process 1 and process 2. And let's say both of them are using clib or stdio or whatever. So at the time that they use that function in that library, the operating system might map different virtual ranges for these two processes to. So, and then if, let's say, this is memory, this is physical memory, and let's say I have this library here residing in physical memory, so I might map different virtual address ranges to the same physical memory range. So there is no guarantee that these two will get the same range in their virtual address range. Now, once I have my executable image ready and I bring it to memory, then again, if you remember, this is a recall. The cycle of execution is you fetch an instruction. So the first thing you're going to do is fetch the instruction. You're going to then decode the instruction and then execute it, see what the instruction is, and then you execute that instruction. And if there are any results to be written to memory or read from memory, then you do that. And then you update your PC to the next instruction, and then you repeat. So this next PC is usually either the next instruction in the list, or you're going to jump to a function, or you're going to jump to, or if it is a for or while loop, you're going to jump back to another instruction. So you're going to redo the instructions that you were doing. So for every single instruction that we execute, we're going to go to memory at least once. And in some cases, more than once. If the instruction that we're executing is a load or a store, we're going to go to memory even more. So far, it's been kind of like a reminder of what we talked about in the operating system concepts. Now, when it comes to protection, what we really want is these addresses that programs generate during their execution. We want them to be, we want these accesses to the memory to be protected. We don't want to allow a single program or a single process to be able to access the data for another process when it's not supposed to do so. Now, if you remember when I was talking about the history of operating systems, the first operating system that we talked about was a uniprogramming operating system. So basically, there was only one program running in the system. If you remember that big IBM device that I showed you, so there was actually not much of an operating system. There was the operating system was kind of like a system library, if you wish. So there was, at any given time, there was only one program running in the system. So in this case, there is no kind of point in protection. There is only there's no point in protecting different processes from each other because there is only one of them. So in that case, you could just allow the program to access physical memory. So there is no harm in that, sort of, because there is only one program running. So that program could have access to the entire physical memory. So when you had uniprogramming, you basically didn't need protection and you didn't need translation, meaning that you didn't need to map virtual memory to physical memory. So from now on, whenever I talk about translation, I'm talking about getting a virtual memory and then figuring out where in physical memory this virtual memory is mapped. So then the next step in the evolution of operating system was multiprogramming. Now, early systems, when we had multiprogramming, they kind of provided the first approach when we moved to multiprogramming was to basically make sure that each process is mapped to a certain region of the physical memory. So give a certain region of physical memory to each process. So for example, in this figure that you are seeing, we would give this region to user process 1, and then this region to user process 2, and the rest of it would be the operating system. Now, in early systems, again, there was no notion of virtual memory. There was no notion of mapping between virtual memory to physical memory. So although we were mapping each process to different regions of the memory, they had access to everything. This is very similar to your labs right now, because whenever your programs ask for memory, they're given access to the entire physical memory. And we're mapping them in different regions of physical memory, but that doesn't prevent them from accessing anywhere they want. They can actually alter the operating system. They can alter different tasks' memory. Nothing prevents them. So the system that you're designing doesn't really have memory protection. So it just assumes that users are well behaved and they're not going to go mess up with different tasks' memory. And this was the case back then when we had multiprogramming at the beginning. And one of the systems that this actually was basically deployed was Microsoft Windows. The early versions of it were working like this. Well, this doesn't sit well with human nature, because you have those who are not happy and they want others to be unhappy as well. So they go and mess up with each other. And this system as is doesn't prevent them from doing that. So this doesn't provide any protection. So if one of these programs are malicious, is malicious, then they can go and mess up with the entire system. And you don't actually need to be malicious. You could just have a bug in your program, and that bug could just go and mess up with the operating system, could go and mess up with other programs in the system. So this is absolutely not safe because you don't have any protection. So one of the early designs was to provide protection, but still use physical addresses. So we could still use physical address or let the programs use physical address, but still provide protection. So how would we go around that? So the solution for providing protection, one of the first solutions was the introduction of two registers, basically the base and the limit register. So these are two extra registers that were introduced in hardware to provide protection. Now, the way it works is not only we're going to map different processes to different regions of physical memory, we're also restricting them to stay within that limit. So when the operating system, when the linker, when the loader loads the program, it puts it in a specific memory region. But after doing that, it also sets this base and limit registers. So it says that the base address, the beginning for the lowest address that this process can access is this, and the size of this process is this. So if this process tries to access anything, any memory below the base or above base plus limit, so anything above base plus limit or below the base, then the hardware would detect that, because the hardware can just look at these two registers and say, okay, you're below this base or above the base plus limit, so I'm not going to allow this access to go through. So the hardware would then raise an exception. So this way, we sort of get protection because we're restricting each program to a certain region of memory. And if different programs are put in different regions, then, well, we have protection. And we're doing this without the use of address translation, because we're still allowing programs to use physical address. And with physical address, there is no translation because there is no virtual address. Now, what is the downside of this? If we want to discuss very, very briefly, I'm going to just say the downsides of this. So one of the serious downsides of this is that it's too restrictive. It doesn't allow any sharing, right? And we'll come back to this later on when I talk about a similar idea with translation. I'll mention why this might not be perfect for sharing. But generally speaking, it's very restrictive, right? To map the programs to certain address spaces and don't allow them to go beyond that address space. Now, if, for example, your heap or your stack want to expand, right? Because you don't know at the beginning, you might have an idea about the size of this program, but heap and stack are dynamic. If you have, for example, if you have a recursive program, you might need a lot of a stack. Or if you dynamically allocate a lot of space, you might need a lot of space. Now, with this base and limit, you're limited to this space. So if you want to go beyond this, then the operating system should get involved, probably copy you somewhere else, and then increase your limit. Again, we will come back to this when we do the same idea, but with translation. So I'll explain these in a little bit more details. But again, this is very restricted. Now, what we really want to have, and what will really address all the constraints that we have, is to be able to use virtual address and do translation. And by doing this, we're able to actually provide protection and sharing. One of the things that I mentioned at the beginning of memory management was, although we want isolation, we also want sharing. So address translation is the solution that we're going to use. It's a tool that we're going to use to get both of them. So we're going to get isolation, and we're also going to get sharing. And again, so this is a recall. I mentioned this when we were talking about the 4 operating system concepts. The idea of translation is we're going to make every process generate its own virtual address. So whatever address a process is generating is going to be local to that process. Then we'll map those virtual addresses to physical regions in physical memory. And as long as I make sure that 2 different virtual ranges from 2 different processes are mapped to 2 different physical regions, then these 2 processes have no way to read each other's data, because this process is going to generate its local virtual addresses. This process is going to generate its own virtual addresses. And if I map them to different physical regions and keep this map protected, so the user program has no way to alter this map. So this map is set up by the operating system. So as long as I then keep these maps protected and don't allow users to mess up with these maps, then I can protect them from each other by mapping them to different regions of physical memory. This also allows me to provide sharing, because then I can map 2 different virtual addresses to the same physical region, and this would allow 2 different processes to share data. Now, in the coming slides, we're going to go deep into how we can implement address translation. So now that we know we can get protection, isolation, and sharing with address translation, we're going to talk about different implementations of address translation. How can we efficiently implement virtual to physical address translation? So that's going to be the topic that we're going to talk about. So again, this slide basically puts together all the benefits that I just talked about. It allows us protection, it allows us memory sharing, and it also allows each compiler and linker to act independently without thinking about where in physical memory the code is going to go. So if you don't have virtual memory, and if your program is going to use physical memory, then the compiler should be aware of where this code is going to reside, because then it's going to generate, or the linker will have to generate addresses that are accurate, physical addresses. But if you use virtual address and say, okay, you can just create your own virtual address without any regard of where in physical memory they reside, then the compiler is completely independent, and the linker is completely independent of the actual reality. They can create any address they want from 0 to 2 to 32 or 2 to 64. And then the rest of it is by the operating system to map those virtual addresses to physical addresses. So it also gives us independence when we are compiling or linking our programs. So these are the benefits of address translation. Now, this comes with a cost, and the cost is performance, because now we're gonna, every time we want to go to memory, and when I say every time, I mean with every instruction we're gonna go to memory, because at least we're gonna read the code for this instruction. So every access to memory now requires a translation, because the process is going to generate a virtual address, and the hardware has to figure out where this virtual address is mapped to in physical memory to go to that physical memory and read or write whatever it wants to read or write. So this will come with a performance overhead. Now, for every instruction, we need to translate. And one way to do this is to do it in software, to do this translation in software, basically allowing the operating system to, for example, interpret every line to see what the address is, but that's going to be really slow. So if we then want to do this in hardware, this would mean that we need to add extra hardware for this because we want performance, right? You have to remember that the reliance on hardware is for performance. So we have an idea. This is how we're going to do it. But then if we do it in software, it's going to be really slow. So we need hardware support. And hardware support means more hardware, and more hardware means more power consumption. And we already know that we have a power problem. So this is the downside of address translation. Now, to just point out, the address translation usually is common in general purpose operating systems, and physical memory, basically not having virtual memory, is very common in embedded systems. So if you, like, for example, the system that you're designing, or if you're designing an operating system for a satellite, or if you're designing an operating system for a robot, you're the designer of the operating system, and you're the designer of any application that is going to run on that device. So you usually don't need protection because you're the only user of the system. So that's also important to be pointed out. Okay, now let's start with the first implementation of address translation. The first implementation of address translation is very similar to the idea we saw before with base and limit. So the way it's going to work is, instead of having a base and limit for each program and allowing each program to generate physical memories. So basically the program generates physical memory, physical addresses, and then I compare the physical address with the base, and then I compare with bound, and then I make a decision if this was okay or not. I'm going to allow my program to generate virtual addresses. Then I'm going to take, let's say I want to put my application in a certain region of physical memory. Let's assume that I'm going to map this particular program to address 0x1000000 to 0x110000. So if this is the range that I want to map my program, I have to note that my program is going to generate addresses from 0000 to this address. So my program doesn't know where it's going to be mapped. So that was the entire idea about virtual memory. So my program doesn't care It's going to generate addresses from 0 to the max address. Now, in order for me to map that to physical memory, I put this address, the base one, in my base. So I put the base and I set the bound. So far, very similar. So this part is very similar to what we had before. It's just how we're going to use it that is different from the previous one. The way we're going to use this base and bound is we're going to get the virtual address and we're going to check it with the bound. And we're going to make sure that all the addresses that we're creating are inside the bound. So all of the addresses should be less than the bound, right? Because the addresses are being generated from 0 to some max. So we want to make sure that all these addresses are less than the bound. So this is basically the size of your virtual address space. You want everybody to be less than this. So if they're more than this, then you raise exception. And you're going to use the base to add to the virtual address, because the virtual is going to come from 0 to the max. But then you have put this guy in a certain address. So you're going to add the base to all the virtual addresses to then get your physical address. So now you can see the translation. This is how the translation is happening. So you get your virtual address. In order for you to translate it to physical address, you're going to add your base, and that's all you do. So for any translation, you just add the base register to your virtual address. Again, compare this with the idea that we talked about before. In that case, we didn't have virtual address. So all we would do is we had a physical address generated by the process, and we would have to check it with the base. We wouldn't add it to the base. We will have to check it with the base and make sure that it's more than the base. And then we had this limit register, which we would use to make sure that the address is also less than base plus limit. Now, in this one, where we have a virtual address, to translate, we just add it to the base. So this is very simple scheme, very simple. Now let's talk about the benefits and the downsides of this. So each process is given the illusion that it's running its memory from 0, 0, 0 to the limit, whatever that limit is. So they don't have any idea about the physical arrangement of their process. So they don't know where in physical memory they reside. This is good, as we discussed. Now the compiler can generate any address it wants from 0 to the max without any regard of where it's going to go in physical memory. In this particular implementation, we are requiring each process to be mapped to a contiguous region of physical memory, because we have a base and bound. So you have just this region for yourself, but all the physical addresses that you get are sequential. So you have a sequence of contiguous memory bytes for yourself. Virtual addresses are independent of physical addresses, so no matter where in physical memory you map your process, you don't need to change any virtual address. So virtual addresses are independent from physical addresses. Now, the upside is we're going to get protection and isolation, and the translation is low overhead. So all we need to do to translate is to add the base and compare with limit. Very simple. So when the address translation is simple, this means that you don't require a lot of hardware and you don't get a lot of performance overhead. So these are the upsides. Now, downsides. We talked about this extendable or expandable heap and stack. So what happens if your program wants to expand? Well, if your program wants to expand, then you have a lot of things to do, right? You have to find another contiguous region of memory to map your program to it. You then have to change the base. You have to change the limit. So a lot of things have to happen, right? You have to search for the memory. You have to copy everything again. So you have to copy the entire range. So let's say your range was from address 0xc to 0x, I don't know, cb. Now you have mapped it to another region, a bigger region. Now you have to copy everything into this region and then set your memory limits and the base. So all of that is going to take a lot of time. Sharing is not possible, right? You cannot share because let's say this is process 1, P1. So here is a stack for this process. You know, so if this is the range for this guy, I possibly could, you know, put two regions and make them share some space. Let's say this is going to be process 2, P2, but you know, at the beginning of P2, I'm going to have the stack. So the stack of P2 is going to be here. Now, where is the bottom of this for P2? So P2 has probably its code here. So the code of P1 is going to be mapped to the stack of P2. There is no way for you to get the code of P2 mapped to the code of P1 unless you basically give them the same address space, right? So sharing, meaning that giving them an overlap in the regions, is not going to be helpful because what they want to share resides in different address spaces, different ranges of memory. So you're going to be mismatching different regions. You're going to match the code of P1 to a stack of P2, for example, which is not what you want. So sharing, although technically you could have overlapping regions, but this is not going to be a helpful thing for processes to share memory because there's a mismatch. So we talked about this as well. It's hard to move because it requires a copying of the entire region. The last thing is memory fragmentation. I think I have a slides for that. Let me see. Let me check one thing. Yeah. So the last issue with base and bound is the issue of address translation. So I guess we discussed about this interprocess memory sharing, which is not possible. The next one is memory fragmentation. So what is fragmentation? So fragmentation in memory means wasted space. So if you're wasting a space, you have fragmentation. Or let's put it this way: if you have fragmentation, it means that you're wasting a space. There are two types of memory fragmentation. There's external fragmentation and there is internal fragmentation. So external fragmentation means that you have some free gap between allocated chunks that you cannot use. So there's a free memory between allocations that is not usable. You probably saw this in the first part of your lab where somebody frees up a memory, but that memory cannot be used because it's a small than what the new allocation is. So you can't use it. This is called external fragmentation. Another type of fragmentation is internal fragmentation. So with internal fragmentation, you have allocated a certain region to a process, but this process is not using the entire thing. So This is called internal fragmentation because you have allocated a memory, but the one that you have allocated it to is not able to use that memory. And because you've already allocated it, you can't use it anymore. So that memory is wasted. So with based and bound, we will have fragmentation. Now, here is an example of that happening. So let's say this is your physical memory. The operating system is residing on top, and you have allocated these regions of memory to process 2, 5, and 6. Now, let's say process 2 finishes and you free up that memory. So this memory is now available. And let's assume that process 9 comes. And let's assume that you're mapping this with a first fit or something. So you figure out that I have a space and process 9 has come. So I set based and bound for process 9 to reside right after process 5. Now, if later on process 5 finishes as well, now you have 2 regions, 2 free regions in your memory. So basically this process 5 is free and the leftover from process 2. Now, let's say if process 11 comes and process 11 is bigger than both of those 2 spaces. Now, you cannot map memory for process 1. And this is external fragmentation because you have these unallocated or non-allocated regions between your allocations that you cannot use for the new process. So this is like a free space that is being wasted because it's not contiguous, right? With base and bound, we need contiguous memory regions, and now we don't have it for this newly arrived process. So let's move on to the next implementation of address translation. So the first one was based and bound. It was simple, but it had some downsides. The next implementation of address translation that we're going to talk about is a multi-segment address translation. So the idea is to look at the virtual address and have it segmented. And this is actually very intuitive, right? If you remember the layout of virtual memory, we already had these segments. So we had the code segment, we had the variables segment, we had the heap segment, we had the stack segment. So these are kind of like intuitive segments for every program. Now, one thing we can do is to map each segment to a physical region, a contiguous physical region. So basically allow each segment to have its own base and bound. Instead of lumping them all together and giving the entire thing one base and bound, we can give each segment, like a code segment can have its own base and bound. Heap segment can have its own base and bound. A stack segment can have its own base and bound. So that's the idea with multi-segment address translation. So basically, we're going to divide our virtual address space to different segments and give each segment a base and a bound. So that's the idea. Now, in this one, we're going to get our virtual address. So this is what the process is going to generate. We're going to look at the first bits, the highest bits of virtual address to see which segment this is. And then we go to this segment map. Hopefully this is set up by the operating system. When it does the mapping, it says, I'm going to map segment 0 to this range, segment 1 to this range, segment 2 to this range, and segment 3 to this range. Now, as the process runs and generates these addresses, I'm going to look at the segment number and I'm going to look at the map, the segment map, and fetch the base and the bound and do my checking to make sure that this is a valid address and translate it. So I check the validity by just looking at this offset and check it to the bound. If it is within the bound, everything is okay. If it is outside the bound for this segment, then I raise exception. If no exception is raised, then I just add the base to the offset to get to my physical address. So this portion, how we're using base and bound, is very similar to what we saw with base and bound. The only difference is now we have a bunch of them. We don't have a single base and bound for the entire program. We have base and bound for each segment of the program. Now, this segment map resides in the processor, so this is extra hardware we need. With the vanilla base and bound, we just needed 2 registers, and every time the operating system brings a new process, it has to change these 2 registers. With this multi-segment address mapping, we need a bunch of these registers, bunch of these base and bounds. We can just have a map. So this is the extra hardware we need. And every time the operating system context switches between different processes, it has to change all these registers. Very similar to base and bound. Every time you start running a new process, you have to change the base and bound registers for that process. Now, the way our addresses are going to look is basically like this. So whenever we have an address, we're going to look at the first few bits as the segment number, and then the rest of it as the offset. Okay, so let's run an example. So this is this is a system with 16 bits of address bus. So all our virtual addresses are 16 bits. So we have 16 bits for our addresses. Let's assume that this is very simple segmentation. So we have only 4 segments: a code segment, a data segment, a stack segment, and a shared segment. Just as an example, you can have as many segments as you want. Of course, if the more segments you have, the more rows you need in your segment map, obviously. So let's assume that segment 0 is code, segment 1 is data, segment 2 is shared, segment 3 is a stack. And let's assume that the bases are as follows. So the code segment base is 4000, the data segment is 4800, and so on and so forth. And let's assume that these are the limits. So we are given this segment map. Now, given this segment map and given the data in this, let's see how each region is mapped to physical memory. So the first one, the first address range is from is the code segment, right? Because the segment ID is 0. So here we're going to look at the first 2 bits. Because we have 4 segments, this means that we need 2 bits. So the highest order bits, we're going to look at that for segment ID. And then we look at the base for this is going to be 4, and the limit is 800. So from 4000 to 48000, this is the mapping. Then the second one, which is data. So actually, this one is right? So if you look at 4, 4 is 0, 0, no, it's, so this is 4, 0, 1, 0, 0. So if you look at the first 2 bits, it's 0, 1, which is data. So the base for data is 4800, and the limit is 1400. So that's where it's going to go. If I look at 8, it's going to be 0, 1, 0, 0. So the first 2 bits is going to be 1, 0, and 1, 0 is basically 2. And C is 1, 1. What is C? So C is, A is A is 10, B is 11, and C is 12. So 12 is going to be 4 and 8. So C is 1, 1, 0, 0. So if I look at the first 2 bits, it's going to be 1, 1. So it's going to be the stack. So that's the segment ID. And as you can see, the base for this is 0, 0. So it's here. And the size is 3000. So from 000 to basically this end address is 0x3000. You can do for this yellow region as well. The base is this guy, so 0f000, and the limit is 1, so it's going to be all the way to x f. Okay. Now, with this, right? Okay. I guess we're good. So let's run an example. So this is the same piece of segment map as before. And this is our program right now. So these are virtual addresses. This is virtual address. And for each virtual address, I have a instruction to be executed. So let's start executing this. So the first one is we have to fetch this address. So we're going to fetch 0x0240. One thing I forgot to mention, I hope you know this. This is a hexadecimal representation. So this, when you see 0x, it's hexadecimal. And the way to read this is you're going to look at each one of these numbers, and you're going to construct a 4-bit number for this. So basically 0x0 is 0000. 0x1 is 0001. 0x2 is 0010. 0x3 is 0011, and so on and so forth. So all the way to 0xf is 1111, right? So each one of these numbers, you map it to 4 bits. So I got a question. Does the operating system store the base and limit for all PCBs? How exactly will this work when PCBs are switching? That's a good question. So every time you context switch, you have to fill this map. What are you going to do with the old numbers that you're going to kick out? Well, you're going to save those in the PCB. So the PCB will have a section for this map. So every time you context switch, you get the old map, you store it in memory, and then you look at the new PCB and read this map and set the map with whatever the PCB says. So at any given time, this map which resides in hardware in the processor, has the data for the running process. And every time you context switch, you have to save this and read a new one from the new PCB that you want to execute. That was a good question. Okay, now let me get rid of this mess I created. Okay. So let's execute this. So the first thing that we're going to do is we're going to translate 0 to 40. So this basically, if we want to just, I'm going to just do this for this particular one. So we're going to have to look at this. So the first one is 0. So it's going to be 0, 0, 0, 0, 4 zeros. Then the 2 is going to be 0, 0, 1, 0. The 4 is going to be 0, 1, 0, 0. And the last one is 0, 0, 0. So this one is 0, this one is 4, this one is 2, and this one is 0. So these are the 16 bits of my virtual address. Now I'm going to look at the first 2 bits for my segment ID. So that is 0. So this is going to be a code. So for me to translate this, I'm going to add this to 4000. So if I add, so this is going to be a segment number, and the offset is going to be 2400. Sorry, 240. So that's the offset. I go to this table and I see the base for segment 0 is 4000. So I'm going to add this to the offset. So 4000 plus the offset, which is 240. This gives me this translation. So this is my physical address. So I did the translation. Now I go and read this. And what comes is the instruction. So this load, this is the instruction I'm going to get. Now, this VARX here has this address 4050. So now I have to translate this because I'm going to load this memory to register A0. So, oh, actually at this point, I'm not going to load this. So I'm going to just load 4050 in A0. So after this instruction, my A0 register will be equal to 0x4050. We'll come back to this. Then we go to the next instruction. It's 0244. Again, we have to translate it. If you translate it, you will see that, again, it's going to be in the code segment. And then you read it. The read says you have to jump to strlen. So strlen is here. So you're going to jump to this address. So we're going to move 0360 to PC. And we jump to that address. Again, we have to translate this address. If you do the translation, you will see that the translation is, again, so, you know, this guy is the offset. And as we saw before, 4000 is your base. So your translation is going to be 4360. So you will read this. It gives you the instruction. Now you move 0000 to your register V0. So now your register V0 is going to be 0x0000. So now we have changed 2 registers. The A0 register is changed. The V0 register is also changed. And then you go to the next instruction. You do another translation. And this other translation is, the instruction is load whatever is inside memory for this address to T0. Okay, so now we're going to go and look at A0. So this is what we have in A0. Now we have to go to memory with this address. So another access to memory. So I have to translate this. Now, if I want to translate this guy, so the first one is 4. So it's 0, 1, 0, 0. So I look at the first 2 bits is 0, 1. And 0, 1 is data. So the base for this guy is this, and the offset is 50. So this means that I'm going to go to, so yeah, I'm going to get the base, which is 4800, and I'm going to add the offset to get to 4850. So the offset is this 50, the base is 4800, and the translation is going to be 4850. And that, so on and so forth. So this is an example of how we're going to use this map to translate. One thing that I again emphasize is that, as you can see, for each instruction, we're doing at least one translation, which is basically just, you know, looking at the PC and then going to the memory to read that PC. So it's all in this code segment that we have to go to memory. For some instructions like this, I might have to do another translation because this instruction was load B. So I had to do another translation to see what this 4050 address means in the memory. Or if it was stored the same. If I were to store something in memory using a register on an address, I would have to do another translation. Okay, so let's discuss this. Now, this method avoids internal fragmentation, right? Because any region that I'm not using, I don't need to map it to the memory, right? And I have a smaller segments. So when I have a smaller segments, instead of having this big segment for the entire process, now I have these smaller segments. So I can map these smaller segments to smaller sequences of memory. And when a new process comes, I don't need to find a big chunk of consequent memory regions. All I need is to find a small sequences of addresses in physical memory that are free, and then allocate each segment of this new process to those physical memory regions. So it is very good for internal fragmentation. This is something that some past students for the first time got to know what segmentation fault is. So you've probably seen segmentation fault again and again and again when you run your programs. What segmentation fault is that you have accessed a virtual address that is outside the allowed length of your segment. So if I have given you a length or a size of, I don't know, 2 megabytes for your code, and now you're accessing something above this in your code segment, you get a segmentation fault, right? So basically segmentation fault is when for a given segment, you go above the limit, then you get segmentation fault. It could be for your code, it could be for your stack, it could be for your heap. So for your heap, you might have a limit, and if you go above that limit, you get segmentation fault. Now, sometimes you shouldn't get the program shouldn't get terminated if it accesses something above the limit. So one example for this is for your stack. So the operating system might initially give you a certain limit for your stack, and if you go above that, then the hardware notices that you are, going above the limit that operating system has set for your stack or for your heap. At that point, the hardware goes and wakes up the operating system and says, okay, look, this program is accessing an address above its limit. What should I do? And then the operating system wakes up, looks at what exactly is happening. So with some processing, it might realize that, okay, this process needs more space for the stack. Maybe it's a recursive call and I need to expand the stack for this. Or maybe it needs more heap, so it has to expand the heap. So in those cases, this segmentation fault doesn't lead to the termination of your program. So you're not going to see that segmentation fault error for these cases because the operating system will take care of it and then goes back to executing the code. Whenever you're context switching, so this is where the question was. So if you context switch, you have to save everything in your PCB, and then basically, so this memory is basically your PCB, right? So you have to store all these. Oh, okay, sorry. This is unrelated. So as I said, the segment table is stored in CPU, but on context switch, you will have to save it somewhere because you're going to change it, right? What are the downsides of multi-segment address translation? Now, I'm sorry. So I got a question. How is Stack Overflow handled in this method? Is there some kernel variable to determine the max size of the stack? So as I said, depending on the system and depending on the implementation, but conceptually, when your program runs first, the operating system or the system library doesn't have any idea how much a stack this needs. They might initially give you some amount of a stack. Then if you need more stack, let's say you have a recursive function, then you might end up accessing something above the limit. So at that point, hardware will notice and notify the operating system. Operating system wakes up. Now, if you have hit your maximum limits that operating system can give you, right? Then the operating system might say, okay, I don't have any extra memory to give you. You're above your limit. But if you haven't, then operating system can give you more a stack and expand your limit. So, expanding your limit might mean that I just change your limit. For example, let's say this is your physical memory. And let's say this is your stack currently. And now if you want more, know that stack going downwards. If this memory below your stack is free, I can just change your limit to a new limit here. But if I have already allocated this region to someone else, so if this, whatever comes after your stack, is allocated to someone else, then I have to basically copy you somewhere else, and somewhere else that I can expand. So this memory will be copied here. Sorry. This region will be freed. And the limit will be changed to this. So I will have to change the base and the limit in this case. If I don't have extra space then I have to do a move, and that is going to be expensive. I don't know if I answered the question. Okay. Okay, so we were talking about the downsides of this method. So the first downside of this method is the first downside of this method is external fragmentation. Although it's better than previous method, which is based on bound, where we had this big chunk. Now I have a smaller chunks and I can allocate them. So I have mitigated the external fragmentation issue, but it still exists. So I haven't completely gotten rid of external fragmentation, because I still could have free memory regions that do not fit a single segment. So the problem is still there. It's not completely resolved. The second one is, if you either a new so if you swap, I guess I'm gonna keep this one to when I talk about swapping out, and then I probably, if I don't come back to this, just mention it. I will come back to this to explain what this means in the future. So let's move on to the third option. So I have another question. Could you please go over what must be saved, restored on context switch again? Does each process have its own segment table and thus needs to be saved elsewhere other than CPU on process switch? Okay, so yes, as I said, segment map is stored on the processor. So this requires some extra hardware in the processor. The operating system sets it for each new process that needs to be run. Once a process is done and we want to context switch and bring another process, we'll have to save the content of this segment map somewhere, because we're going to change it to the new process. So where you save it, well, one option to save this is in your PCB. So you can save the content of your map in your PCB. And if you do so, then the next process that is coming also has this information in its PCB. So I can read from the PCB and set the map. So where is the segment map? It's in the processor, it's in the CPU. Where do I store it on a context switch? Whenever I context switch, I have to save it somewhere. And one option is your PCB. You can save the content of this segment in your PCB and then read it from your PCB to the map. So hopefully I answered that question. Okay, so next, what time is it? 3:48. I have 2 more minutes. I don't think I can continue with this. So let's pause here. I'll continue this from. So we'll continue this next Tuesday, hopefully. So thank you for attending the lecture, and take care, be safe. I'll talk to you on next Tuesday. Bye.